Okay, in American baseball, during his 24-year career, Ty Cobb, this gentleman here, captured 11 batting titles, and on his retirement in 1828, he held many baseball records, including the most games played. Today, he is largely remembered, though, as having the record for the highest career batting average. It still stands today. On average, Ty Cobb made it to bat 4 times a game. His hits per game and how often it occurred is shown in the table below. So the question is, does Ty Cobb's hitting follow a binomial distribution at the 10% level of significance? Well, to understand what's going on here, we have to recognize that what information is missing. And the information that's missing is what is the probability that Ty Cobb actually hits the ball. Okay, so on one game, each game he goes 4 times at bat. Okay, and so on this game here, he's gone 4 times, and basically this is 0 out of 4 attempts, 487 times. This is 1 out of 4 attempts. This is 2 out of 4 attempts, and so on and so forth. So when I want to think about how many times, so in 92 games, he hit 4 out of 4 times. So in total, he hit 4, if I go 4 times 92, he had, in these 92 games, he had 368 hits. Okay, and this is total hits. In this game, we had 0 hits. In these games, he had 1,231 games where he had 1 hit, so he had this many hits. Of the 4 times he went to bat, he had 2 hits 970 times. So to find total hits, it's going to be 2 times the 970, which is 1940. And finally, it's going to be 3 times 255, which I can see is 765. And so the total hits is going to be 1, 2, 3, 1 plus 1940 plus 765 plus 368. Enter. And so we know that Ty Cobb had 4,304 hits in total. We need to find out how many times he tried to hit. Well, I know that if I add up the total number of games, is going to be the total number of games is 3,035, and each time he went up 4 times. So it's going to be 4 times 3,335. So if I go 4 times 3,335, I get. So the probability of him hitting the ball, is equal to 4,304 divided by 12140, which is 4,304 divided by 12140. Which I get a probability. I'm going to store this into alpha A. So I get 0.354 355 to 3 significant figures. And so this is the total number of hits, and this is the number of times he tried, because each game he tries 4 times, and he plays 3,035 games, which is all of these numbers added up, or I can read it from this here. So getting this initial probability of total hits is not straightforward. You have to understand that this is 4 out of 4 attempts, this is 3 out of 4 attempts, and so on and so forth. So now we have the probability of hitting the ball is 355. We need to now state an appropriate hypothesis. So to say the appropriate hypothesis, we want to say the null hypothesis is Ty Cobb's hits per game follows a binomial distribution of 4 is our n with our probability of 0.355. So it fits. We're saying that it fits binomial, whereas the alternative, it does not fit binomial. Okay, and so now that we know that, we have to find the degrees of freedom. Well, I know there's 1, 2, 3, 4, 5 different categories. So my degrees of freedom is going to be 5 minus 1 as always. And because we've estimated this value, it's subtract 1 more. And so degrees of freedom in this case is 3. And so now we have to find our chi-squared statistic and state the conclusion. Well, in order to do this, we have to fill out what our expected values are. And so going here, I'm going to use my binomial distribution. I know my binomial distribution is going to be PDF of 4 trials, and my probability is alpha A, and I'm going to refer to L1 and place them into here. And then going to L4, I know that there's 3,335 games. And so I'm going to go 3,035 times L3. So these are how many games are expected. So he's expected 500 games, 526 games to hit it 0 times, 1,157 1 time, and so on and so forth. And so I will drag this over, and this is we know that this is our expected, and this is our observed. And so we're ready to do our chi-squared test, and so I go statistics, test, chi-squared goodness of fit. Our observed is an L2, expected is L4, degrees of freedom we got already to be 3, and we're going to calculate that. And so here are all the important information we can come up with. And so I know that my chi-squared statistic is equal to 73.84, and my p-value is approximately 0. So if I think about what this means, is if I graph this, here's my chi-squared graph. My chi-squared critical value is 6.251. So somewhere there exists a value here of 6.251, which defines my critical region. If my test statistic is inside the critical region, and this one is clearly inside, here's 73.84, then I will reject H0. And so I'm going to state my conclusion based upon my chi-squared statistics. It says I have to use my chi-squared statistic, and then it says determine the p-value afterwards. But here is my conclusion, and so my conclusion says since my chi-squared is bigger than the chi-squared critical value, then our test is within the critical region, we reject H0. Or I could say the p-value is approximately 0 and less than alpha. We reject H0 and claim strong evidence to say that Ty Cobb's hitting does not follow a binomial distribution. So in doing these problems, a couple things. We have to make sure we clearly understand what we are putting into our calculator, what this frequency table means, and we are using this to find the total number of hits over the total number tried to find the probability of hitting the ball for Ty Cobb. We test that. We know degrees of freedom is our 5 categories minus 1. Subtract the number of estimated parameters, which is 1. We found our chi-squared statistic and made our appropriate conclusions.